Hi, my name is Dr. Abdul Wahab Animoku, and this is my first ever YouTube video. In today's video, we're going to look at a couple of problems on linear transformation, and this is the first of many videos that I'll be uploading on this particular topic. So let's just get started. So this problem is about diagonalizing a linear transformation. And the problem says we should find the characteristic polynomial, the eigenvalues and the eigenvectors, and then we should diagonalize, if possible, the linear transformation below. So how do we approach such problem? So, um, so if you're familiar with linear transformation, you would understand that we can characterize this transformation in several ways, depending on the basis that we use for this, for the domain of this transformation and the range of this transformation. And the most useful ones are the ones that will simplify the matrix of transformation. So for this case, the easiest ones to find would be the standard basis, right? The standard basis for R3. Okay, so what does this mean? For R3, the standard basis would be, so let's call this B, right? It will contain E1, E2, and E3. And what do we mean by E1? E1 is basically the vector 1, 0, 0. E2 is the vector 0, 1, 0. And E3 is the vector 0, 0, 1. Okay, so how do we then use this? So what we do is we first of all, so what the first step in this process is to find the matrix of transformation relative to standard basis for R cube. And this standard basis for both the domain and the range of this transformation. So let's just go ahead and do that. So how do we do this? We first of all find the transformation of these vectors in the basis. So we need to find this first. Right. So when we do this, that means this basically means our x is 1, our y is 0, and our z is 0. So when we impute that into this transformation here, we'll see that what the first vector will be 1 plus 2 times 0, which is just 1. The second component would be 2 times 0 plus x, which is 1. So this is just 1, and then z is 0. Okay, we'll do the same thing for the rest. So T0, 1, 0, quickly, it's going to be 2, 2, 0. And finally, T001 would give us 0, 0, 1. And why is it 0, 0, 1? Is because x and y are 0. So basically, when x and y are 0, the first two components will be 0, 0. And the last component will just be 1 because z is 1. So now when we have this, what we need to do is to also write this vector as a linear combination of the standard basis, because remember we are using the standard basis for both the domain and the range. So because they are standard, because they are, these vectors are quite these vectors are in the standard basis, so it basically means we're going to have 1 E1 plus 1 E2 plus 0 E3, and we can do the same thing for the rest. And you can actually check that, check this to be the case. So, right. So, if you're working with standard basis, you don't actually need to write this right-hand side. You can quickly write a matrix of transformation based on these vectors. So the mistake that most students would make would be, or the most people would make in this regard would be to assume that this is the case for all types of, matrix of transformations. No, if I was to have a different set of bases, different from E1, E2, E3, then I would need to find all of this depending on what these vectors E1, E2, and E3 are, right? So I think we'll look at other problems that use that have this different structure. So now let's let's now write the matrix of transformation relative to the standard basis now. So the matrix will now be, so let's just call this matrix A. It's going to be a 3 by 3 matrix, and what it will do is it takes the rows of each, it takes the coefficients of each row and write it in as a column in this matrix. So the first one will be 1, 1, 0. So it will be written in the first column. The second one will be 2, 2, 0. And the third one will be 0, 0, 1. So now we have the matrix of transformation relative to standard basis. Now that is the first step in trying to diagonalize this transformation. So basically, this is what we have. Now, the theory of eigenvalue and eigenvector is basically trying to diagonalize the matrix such that the matrix that we have would be, so basically this is the big picture, right? So what we're hoping to get is to have a basis. So let's call this new basis E, and this basis would contain 3 vectors, because as you know, for R cube, you need 3 vectors you need 3 vectors in the basis for R cube, right? So if you need 3 vectors, that basically means that those 3 vectors will be linearly independent, and those 3 vectors will also span R cube. So that's why we are looking for this B1, B2, B3, such that what must they satisfy? We look for B1, B2, B3 such that the matrix of transformation that we have would be a diagonal matrix, and we call this the eigenvalues, right? So this is what we're trying to, this is what we mean by diagonalizing. So we're trying to find E1, E2, E3, and the corresponding B1, B2, B3, which will be determined by the solution of the eigenspaces of these eigenvalues. Okay, these are the things that we're trying to obtain. So now let's go ahead and quickly do the rest of the work. Okay, so now we need to find the characteristic polynomial. Now, how do we define this? We define that this is a function of, so let's define as a function of t. This is basically a determinant of the matrix of transformation relative to standard basis minus t I, where I is the we call this the identity matrix, right? Depending on what, so this is the n by n identity matrix. So depending on what dimension of A is, so would be I. So what does this mean? So this basically means we are going to find the determinant of what? Remember A that we got, let's quickly write the matrix again. 1, 2, 0, 1, 2, 0, 0, 0, 1, right? 0, 0, 1 minus t times I, right? So this is what we have, right? And basically this will give us determinant of 1 minus t. So what will just happen is we just minus t from the diagonals of this standard, the matrix of transformation relative to standard basis. So that's what we're going to do. We're just going to subtract t from this, and we try to find the determinant of this. Right now, how do we find the determinant of this? It's basically easy. We can use any row and any column, right, to find the determinant. Now, what we're going to do is we're going to try to use the easiest one. So when you look at this particular matrix, the easiest one will be this column, right? So, actually, it isn't. The easiest one would be to use either the last column or the last row. Okay, so let's correct that. So we're going to use the last column or the last row. So let's just use the last row. So what happens is, basically what will happen is the first entry is 0. Then we are going to have determinant of this, just for future, just so that you understand this and use this for other problems. It's just when we cross out the column this entry belongs to and the row it belongs to. So the rest will be the determinant of that. So that means this. Notice that, and then we put minus in the for the second entry. then we have 0 again, then we find the determinant of the 2 by 2 matrix corresponding to, if we block out the column this belongs to and the row again, we have 1 minus t, 0, 1, 0. And then finally, we have the last entry, which is 1 minus t, determinant of what? So let's finish this. So this is just covering the column 1 minus t belongs to and the row it belongs to. So that gives us 1 minus t, 2, 0, 1 minus t. So let's just correct this. So we have 1 minus t, 2, we have 1, 2 minus t. Okay, so that is what we have. You can see that the first two calculations will be 0, so that's why we are using this in the first place. So what we just have is 1 minus t. So let's quickly do determinant of what? 1 minus t, 2, 1, 2 minus t. Now what this gives us is determinant of this is just when you multiply this column, the diagonals together minus the other diagonal. So it's just this multiplied by 1 minus t times 2 minus t, then minus 2 times 1, which is 2. Okay, so this is what we have. So now we can simplify. The inside, when you simplify this, this is just 2 minus 3t plus t squared, then minus 2. Right. Okay. So what does this give us? This gives us 1 minus t multiplied by what? T squared minus 3t. Okay, then you can factorize t out, so you basically have this t minus 3. Okay, so this is what you have as our characteristic matrix. So don't forget. So this is the answer to the first part of the question, which is find the characteristic matrix. The characteristic polynomial. So this is what you have. So the next thing is we need to find the eigenvalues. And how do we find the eigenvalues? The eigenvalues are the roots of this characteristic polynomial. So find the values of t that will make this polynomial 0, so which means the root of that polynomial. And I think this is easy. This is just when we make this equal to 0, and that gives us t equal to 0, 1, and 3. Okay, so we have 3 eigen values. Now, what do you do next from here? So let's just go back up. So let's take a look at our so let's just take a look at this matrix. So we already got our eigenvalues. We have 0, 1, and 3. Okay, this is quite fine. Now let's take a look at this. Remember, we had to when we're finding the characteristic polynomial, we basically have determinant of this matrix, right? So we are still going to use this matrix to find the solution to the eigenspaces of each eigenvalue. Okay. Now, what we now do is to find the eigenspace or the eigenspace solution to each eigenvalue. We just need to impute these numbers t0 into this matrix, and then see what the homogeneous system, the solution to the homogeneous system is. Okay, so let's just do that next. So when t is 0, what do we have? This matrix turns to what? 1 minus 0, which is 1, 2, 0. The next one is 1, 2, 0, then 0, 0, 1, right? So this is what we have. Okay. Now, this is just the coefficient matrix of a homogeneous set. So coefficient matrix of a homogeneous set. Now, what does this mean? So let's just focus on this. Okay. Now, what does this mean? It means that we can write this as a homogeneous equation, which gives us one. So where the variables are x, y, z, so that will give us 1 times x plus 2 times y plus 0 times z equal to 0. The next one we have x plus 2y again equal to 0. The third one we have 0 times x plus 0 times y plus 1 times z, which is just z equal to 0. Now, the solution of this basically tells us that what x must be equal to minus 2y. From the first equation, you can get this, and then we get that what z equal to 0. Notice that the first and second equations are the same. So basically, the solution to this x, y, z is just when x is minus 2y, y is a free variable, and z is 0. So we can take y out, and we have this. So this tells us that what this vector is the generator of the solution space of this eigenvalue. So therefore, the solution space of this eigenvalue is spanned by this vector, right? So that's the first thing. So this is, and this corresponds to the B1 I was talking about, which is the eigenvector corresponding to the eigenvalue 0. Now we are going to do the same thing for the rest of the eigenvalues. So we could quickly do that. So when t is equal to 1, so we go back to this. We go back to this this matrix. We go back to this matrix again and impute t equal to 1 there. So that will give us what? That will give us 0, 2, 0, 1, t minus 1, that is 1, 0, and we have 0, 0, 0, right? So this gives us that what? 2y must be equal to 0, x plus y must be equal to 0, and then there's no condition on z. So this means that what? If y is equal, so this means y is equal to 0 from here. Now, if y is 0, it means that what? X plus 0 must be equal to 0, which means x is also 0. And z is a free variable. It's anything, basically. There's no condition on z. Okay. Now, with this, the solution set is just going to give us XYZ solution set is going to give us 0, 0, Z. And we can take the Z out, that was 0, 0, 1. So the eigenvalue, the eigenspace would be spanned by this vector 0, 0, 1. So this would be the vector, eigenvector corresponding to this eigenvalue 1. Now, finally, let's go to T3. So when t is 3, what does that give us? So again, we input 3 into this matrix here, right? So we can focus on that. So when we replace 3 with this with the matrix that we have before, what does that give us? So that is 1 minus 3. So 1 minus 3, that is minus 2, 2, 0, 1, 2 minus 3, that's minus 1, 0. And the last one is 0, 0, 1 minus 3, that is minus 2. Okay. Okay. So we have this. So what does this tell us now? So let's zoom in and focus on this. So this tells us that what? We have minus 2x plus 2y equal to 0. And so what else? So let me increase the, okay. What else? It means we have x minus y equal to 0. And finally, we have minus 2z equal to 0. Now, okay, so okay, so what does this give us? Basically, the first and the second equation are the same. If you divide the first equation by minus 2, you would get the second one, basically. So this tells us from here, we know that what z must be equal to 0. And here, from here, x must be equal to y. In fact, that's all we need to get the solution set. So x, y, z will be x is equal to y. Y will be the free variable. We could also choose x to be the free variable if you'd like to go that route. The answer is the same. And then this gives us 1, 1, 0. Okay. Now that you have this, What does that mean? So it all means that what the solution space for this eigenvalue would be 1, 1, 0. And we're pretty much done. It means that what our eigenvalues for this transformation are basically 0, 1, 3, and the corresponding so we said it was E, the corresponding eigenvectors. We can go back and corresponding to these eigenvalues. So the first one is -2, 1, 0. The second one that we got was 0, 0, 1. And the third one is what? 1, 1, 0. Okay. Now, what this means is for the transformation that we're considering, under consideration basically, the matrix of transformation can now be written as what? Can now be written like this, where the diagonals are the eigenvalues. Everything else would be 0. Relative to this, relative to E as the basis for both the domain and range of this transformation, right? So this whole method is just to change the way we think about the transformation relative to the standard basis, and we convert that to a new set of a new matrix which has its own special combination of vectors as the basis. And if you do, you can just as an assignment. So what I will expect you to do is this as an exercise. Try this. When we use these three vectors for matrix of transformation. So when we use these vectors, so basically what I'm trying to say is once we have this, put -2, 1, 0 into the transformation, you get some vectors, right? The same thing is 0, 0, 1, you get a vector. The same thing with 1, 1, 0, you get another vector. Now try to write this vector as linear combination of these vectors, right? Remember we said we are using this basis for both the domain and the range of the transformation. So try to write this, right? So this is your homework. So here will be 3, 2. So try to write this for, so let me just complete this. And A 2, 3 plus A 3, 3, 0. Now try to write this, find this vector, try to write this as a linear combination of these three vectors, and you would come to see that what basically the matrix of that transformation would be exactly this one. So this is basically the purpose of diagonalizing a transformation. I hope this helps you. Please, you can stop anywhere in this video, go back, rewind, do what you have to do to make sure you understand this concept. We'll be having more of these problems in later videos. Please try to subscribe to this channel, like and comment. I would like to see your comments. If there's any part that you want an elaboration, I'll be happy to reply to your comments. And then press the bell button so that you can see, you can get a notification anytime I post a new video. So I will be seeing you guys on the next one.